Good morning, everyone. Welcome back to our usual Monday seminar. And our today's speaker is Nikolai Prochorov from Universite Aix-Marseille. And he will tell us about dynamical approximations of a singularly finite maps.
Thank you for the introduction, and well, thank you a lot for giving me this opportunity to give a talk, especially in person. Thank you for hosting me in Warsaw. And well, having this opportunity, I also would like to thank the organizers of the conference that was last week. Well, later is better than never. So yeah, and I'm going to talk about joint work in progress with Mukundan and Reinke. And as Kostya already mentioned, the title of this talk is Dynamical Approximations of Postsingularly Finite Entire Maps. So, well, as you may guess, I'm going to talk about dynamics of entire maps in this talk. Well, first of all, I'd like to set some, simple notations and conventions. Of course, when we talk about dynamics of entire maps, we care a lot about singular values. And by S sub index F, the set of singular values of entire map F. And well, as we know, like dynamics of transcendental maps can be very, very wild, very diverse, very complicated. I don't know, last week we had talks about, lengths of water wandering domains and different Baker domains with or without periodic points on their boundaries. So sometimes it's complicated to work in full generality. That's why we want to restrict ourselves to reasonable subfamilies. And for this talk, such a subfamily is going to be class S, or maps of finite type. So all our maps are going to have finitely many singular values. And as I already said, when we have an entire map, there is kind of meta statement saying that dynamics of singular values defines the kind of global dynamics of map. And that's why we care a lot about actually like orbits of singular values, and that's why we denote postsingular set as a complete forward orbit of singular set. And one may start from considering the case when the dynamics singular values is well, as easy as possible. Like every singular value is either periodic or pre-periodic. This assumption for maps of finite type means that just this postsingular set is finite. And well, this leads to the definition of postsingularly finite entire map. Of course, I said like dynamics of singular values as easy as possible. Of course, it doesn't mean that postsingularly finite maps are easy, but I'll try to say to motivate why actually we care about these maps, because one can say, well, this is a very strong assumption that every singular value is periodic, and maybe these maps are too rare, and well, this is some, pathological case. Indeed, one can prove that there are countably many postsingularly finite maps up to affine conjugation. So in a way, there are not too many of them, but there are two reasons why we care. The first reason is that, well, indeed, this is a strong assumption. These maps have strong properties. So why not to study them if we have such a strong property? Well, we can having strong assumptions, we can prove strong theorems. Another reason is that they are kind of structurally important. Well, the easiest probably example is was from Mandelbrot set. Well, if you know that every kind of hyperbolic component of Mandelbrot set has its center, which corresponds to postcritically finite polynomial. And in fact, if you believe that Mandelbrot set is locally connected, we kind of can describe its structure by just looking on post-critically finite polynomials. So this is for polynomials, at least, that's very important. So that's why in this talk, I'm going to focus on post-singularly finite maps. And just to give you some examples, Of course, we can find a lot of examples in polynomial world, for example, like Basilica map. But well, there are just for you some examples from transcendental world. We can take this, for example, map from exponential family. It has a unique singular value 0, which is maps to pi I by map f, and then to minus pi I, and then minus pi I is, I guess, fixed. And well, there are another example of map. Now it has one asymptotic and one critical value, and they are actually fixed by this map. So this is just some examples. Well, when I said all the, I don't know, notations and so on, and I like to speculate a bit about the following idea. Like, we know that all entire maps in numerical sense can be well approximated by polynomials. For example, we can take just Taylor polynomials and obtain such approximations. But it's not clear whether these approximations are actually mean something from dynamical point of view. So of course they are numerical, but it doesn't imply that they have some dynamical meaning. And well, can we actually produce some, I don't know, approximations of entire maps with polynomials so that these approximations will have some not only numerical properties, but they will have some, I don't know, meaning for the dynamics. And especially this kind of question reasonable for maps of finite type, because they kind of not too far from polynomials. They don't have pondering domains, they don't have Baker domains. So of course they are much more different and much more complicated than polynomial family, but somehow we can raise the following question. And I just will briefly comment why we can't hold that if you just take a map and take any approximated by polynomials, or just approximated by polynomials, then this approximation will have any meaning. Well, because when we have two maps such that we have some point, suppose we have some point and we have two maps such that their values at this point are very close. So it doesn't imply that the orbit of this point by these two maps will stay close. Especially we cannot expect such behavior when the point we have chosen belongs to Julia set of one of the maps, because then dynamics is very unstable and doesn't it changes a lot under small perturbations. And well, there are some, for example, there is a difference in Julia sets, well, for polynomials and transcendental maps. For transcendental maps is unbounded, and for polynomials it's bounded. And moreover, if we go to postsingularly finite context and we look at maps so that every singular value is strictly pre-periodic, then the Julia set of such map is the whole plane. For example, in the exponential context, if you have postsingularly finite exponential map, then, well, it's only singular value 0, it's a meted value, so it cannot be periodic, it's strictly pre-periodic. Then the Julia set is the whole plane. So we have like a lot of kind of different maps from exponential family, but all of them are very chaotic. So the Julia set is the whole plane. That's why we cannot expect that like we approximate them and having numerically close values, it will mean that the orbits will be similar. But this is just some hand waving to explain that this question is not that trivial as it could be. And well, but however, we are not the first who are asking this question. I think the first work was by these 6 people, and they asked this question for exponential family. Well, as usual, people start from exponential family, and they were interested whether this limit, which is like from, I don't know, high school or something like this, whether this limit has any kind of dynamical meaning. And I'm not going to talk a lot about their results, but they proved something like that dynamical rays for this polynomial, they in certain way converge to dynamical race of hairs for exponential length, and similar result for parameter spaces. So in a way, they prove that this limit it has well, it's not just a kind of numerical limit, but in fact it has some dynamical meaning. And as I said, that's not something we can a priori expect. So this limit is kind of very good, not just numerically. And well, I have to say that more people worked on this problem. Well, some of them you can see here, maybe some of them I missed. Well, some of them also looked on some particular families like exponential maps. Some of them tried to investigate which properties, dynamical properties holds or don't hold for approximations. So this is a short kind of a review of previous results. Yeah, but in our case, we work in post-singularly finite context. So all our maps are assumed to be post-singularly finite. And maybe I'd like to formulate one of the main theorems and motivate it so that like the final goal of my talk would be clear. So what this theorem says? Well, suppose we have an arbitrary post-singularly finite entire map, and well, the theorem says that there exists a sequence of post-singularly finite polynomials, Pn, so that first of all, well, these post-singularly finite, post-critically finite polynomials, they converge to F. So it's already something non-trivial because we have not just convergence, but F and polynomials Pn, they share this property of being post-singularly finite. And moreover, well, this dynamics of Pn on its post-singular set is conjugated to dynamics of F on its post-singular set. Means that kind of they are singular orbits of their singular points, singular values behave in the same way. And well, now I'd like to speculate a bit why it's kind of meaningful and natural and so on. Well, of course, as I already mentioned, all our maps are post-singularly finite. And basically what this property means, it means that their singular values behave in the same way. Moreover, we can actually prove that, well, they will be not only conjugated, but they will converge. So singular set of Pn will converge to singular set of F, and post-singular set of Pn will converge to post-singular set of F. And we know like that in the dynamics of entire map, one of the kind of most important parts is actually dynamics of its singular values. And this theorem says that basically combinatorially dynamics of singular values for Pn and F, they are basically the same. And this also says that basically like orbits orbits get close to each other. So like in a way, this is core dynamical part is really dynamics of singular values for entire map. And here we have that basically this kind of core dynamical parts for Pn and F, they are the same, or they're getting very close. They kind of yeah, so what I want to say that this kind of
Julia sets
yes. Yes, in fact, Julia says will converge in Hausdorff metric, but this is actually true in even more general. It was, I think, proved by Kisaka. He proved that if our maps are nice enough, kind of semi-hyperbolical, I don't remember, then the Julia says will converge.
Continuity is clear. Periodic orbit, hyperbolic, those that on the bad. have the same periodical close enough.
Well,
This is semi-continuity. Because one reminds a divorce situation where there's no continuity from the right side. So that's why I asked.
so in general, well, it's if we just take some entire map and approximate it by other
But
time.
it is hyperbolic.
Yeah. So here, well,
Divorce is parabolic.
yeah. So here,
Close to this point.
yeah. So of course, in the very arbitrary case, well, Julia says do not converge to each other. But if maps kind of hyperbolic or something like this, then yeah, indeed, not necessarily post-singularly finite, just hyperbolic. Then there will be convergence, as Julia says, and I think Kisap proved it. But of course, in the arbitrary situation, yeah, we cannot expect it. But here we have actually more. We have that like the, I don't know, core part of dynamics almost the same. Well, actually, we can even a bit make this part stronger. We can say that this conjugation preserves if some singular or singular point is actually singular or critical, then this kind of conjugation preserves it's this property. Well, maybe I can even draw some picture. So really, if we have our map F, so it has say three post-singular points, and here is the domain of our map F, and here is range. And if we take like small disks around them, well, then for sufficiently large n, both critical set of our polynomials will look like this, will be in these small disks. And basically, well, this point there will be kind of, well, first of all, their orbits will be very close, but also they're kind of, say, if this is a critical point, then this point will be also critical and of the same degree. So kind of morally, this is this kind of 2 points for entire map and for polynomials will be very close. And maybe just one more remark is that what we can get also from the theorem is that if you take a curve, well, when we talk about post-singularly finite maps, we like to talk about curves sometimes, and curves kind of relative post-singular set. So if we pick some curve alpha, and well, if we take its preimage by map F, there will be, well, if F is transcendental, there will be infinitely many lifts of this curve. There will be maybe, I don't know, something like this, or something non-closed, whatever. And then if we pick, if we fix curve alpha and fix its preimage, say alpha prime, then for sufficiently large n, if we take a preimage of this curve by polynomial Pn, there will be kind of lift of the curve alpha by polynomial f, say alpha n prime, which will be kind of in epsilon neighborhood of alpha in particular. And moreover, alpha n prime will be closed if and only if alpha prime is closed. And for example, here we will have something like that. In particular, these curves, they will have the same homotopic classes relative to these disks. So in a way, well, in all this post-singular dynamics and sources theory, we really care what web does with our curves. And here, like, it's in a way, it's sort of combinatorics of map, we can think about it. And here, it means that kind of combinatorics of polynomials Pn will look more and more like combinatorics of F. Yeah, so this is just like 2 points of view on this theorem. I hope I ensured you a bit that these approximations, at least in post-singularly finite context, they are, well, some dynamical meaningful, some dynamical meaning. And maybe a brief comment why it can be interesting. Well, first of all, it's very nice to have something that works well for post-singular finite maps, but for all post-singular finite maps, rather than for, I don't know, exponential family or something like this. And also, I think, well, at least I think all we like post-critically finite polynomials because probably it's the most well understood family, and there are a lot of nice things developed for them, including like Hubbard trees or spiders or external angles, iterated monodromy groups, and a lot of kind of in a way combinatorial tools that work very nice for post-critically finite polynomials. And now we want to move further. We want to obtain something for transcendental maps, and some things that were known for polynomials for a long time. They were generalized for intranscendental context, but some were not. But kind of this theorem, I don't know, it provides some hope or invitation that probably since post-singular finite time maps, they are dynamically meaningful limits for post-critically finite polynomials, and provide certain hopes that maybe if we were very successful in developing different theories for polynomials, post-critically finite polynomials, hopefully we will, I don't know, succeed in a way in transcendental context as well. Yeah, so this is just like, for you, I stated the main theorem and a bit like waved my hands and why should we care? And well, so, and further I'm going to go into kind of detailed discussion, but before it, maybe you have any questions?
This is what you described in the picture. Is it a sort of defining property how you construct this polynomials to really approximate this approach, just like a sequence of your construction?
Well, that's a good question. In fact, this idea is related to how we construct it. Not exactly like this, but I will explain it later. The idea, and yeah, indeed there is certain way, but yeah, but in fact, this property you can actually just obtain from having the theorem, but really it's related to the way how we construct.
So do you have, do you believe there's any chance of generalizing this into rational maps in the remotely?
Well, that's a reasonable question, and I think so.
Yeah.
I haven't checked it yet, but we believe that that it should work also in a remorphic context. Well, maybe with some extra difficulties. But as usual, but the hope is we will be able to generalize it for meromorphic and rational maps. Cool. So let me move further, and well, to discuss further details, I have to dive a bit into sourceless theory. Well, I'll try to give very quick introduction to sourceless theory in complex dynamics. And I'll start from just example. So here we have a quadratic polynomial, which has unique critical point 0, which is 3 periodic, and in fact it's so-called rabbit polynomial. And I'll start with drawing this picture. Normally people draw a Julia set of rabbit polynomial, but this is like very bad approximation of Julia set of rabbit polynomial, but it still looks a bit like rabbit. But what actually
is 1 year bigger than other.
Well, this is topological rabbit, so so what I'm proposing to do, so here we have kind of a domain of our map and range of our map, and in both domains and range, I labeled the post-critical set, and here we have kind of fat cross, which is critical point 0. And what I'm doing, I'm taking this kind of, I call it rows graph in the target of our map, and I'm taking a image. It will be well this kind of rabbit-like graph, which covers actually initial graph. And well, so yeah, and this is what this picture means. And well, one can say that it's a silly picture, but in fact we can read some information from it. For example, we can understand if we forget that our orbit of critical point, then we can actually read it from this picture, because we know that this is our critical point. It's surrounded by red edges, so it has to go to this petal with red boundary. So on this point, it's the same as this point, and it's with blue edge, so it goes here, and well, we can reconstruct the orbit. Also, well, it's not exactly a coincidence that it looks like a bit like Julia said. I'm not going to talk about it, but just to say that this picture is not so useless as it might seem. In fact, we can go further. We can, for this graph, we can add these kind of curves, joining infinity with center of rows graph, and joining post-critical points with the center. And also we can take pre-images of these kind of curves, and we are getting this graph. And actually, well, this graph, what's nice about it is that on every face of this graph, our map is homeomorphism. Well, in fact, by homomorphism. So, for example, I don't know what kind of this face is mapped to kind of here by homomorphic and well. So, and this is something like, so, well, I don't know, at least this has some meaning that we kind of decompose our plane so that our map is homeomorphism on each piece. So it's kind of, our map is piecewise homeomorphism, if you wish. And yeah, this in source code theory, normally such kind of pictures, well, they are very, well, they are very popular, and normally they are called, I don't know, combinatorial models of our maps. And I'll try to say a few words why actually in source code theory people care about these pictures. Well, one of the reasons is that there is some problems that are kind of easier to solve having such picture than having a formula. Of course, not all problems like this, but in source code theory, such problems appear. And another argument is that, well, in fact, I will state it strictly, but this picture, in fact, it uniquely defines this polynomial. In fact, so this is maybe it's not clear what I mean for a moment, but I will state it in a precise way. So in fact, we don't lose any information when we go from formula to such a model. Well, there is another question: which kind of properties are easier to digest from this picture, and which are easier to digest from formula? But well, that depends on in which property we are interested. Yeah, and well, the second reason is the following. So in holomorphic dynamics, we normally need graph kind of problems where we need to construct a holomorphic map with some dynamical properties. And there are various tools to do it. For example, I don't know, quasi-conformal surgery or approximation theory. And in fact, source code theory also provides such tools. Well, normally in post-singularly finite context, but not only. So the basic idea is that like holomorphic maps, they are sometimes very rigid, but topological maps, they are very, very flexible. So and basically this picture, it can be viewed as topological model as well. It's not very meaningful to study point-wise dynamics because we don't know if I pick point, this picture doesn't tell me where it goes. But I know that on this piece is mapped homomorphically to that piece and so on. So it really like combinatorial or topological one. And well, sometimes we have a situation that we need to construct some map with some, I don't know, prescribed properties. And how we do it? Well, we start with drawing pictures like this. And in a way, sometimes it's very easy because these are very kind of topological pictures. It's like, I don't know, kindergarten drawings or something like this. But then we need to prove that, of course, when we want to construct a homomorphic map, we need to prove that basically this kind of topological picture is realized by some homomorphic map in some precise sense, which I will say later. So, so here, for instance, we started from this homomorphic map and we obtained this combinatorial model. But in reality, sometimes we go in different directions. So we first draw some pictures like this, and then we are trying to show that there is a homomorphic maps that actually realize this construction. Yeah, so this is some kind of motivation in a way for social theory why we actually care about these things. Yeah, and maybe further I'll give precise definitions, but just I'll give one comment that this map, this construction, as I already mentioned, it does not define uniquely. If we forget that we started from rabbit polynomial, this construction does not define uniquely our map. So we know that this something maps homomorphically to another kind of piece. So we have to kind of choose finitely many homomorphisms. We have to glue them along the boundaries, and it defines map. But kind of we can choose different homomorphisms and get different maps, realizes this picture. And so, but in a way, we want to say that well, this picture defines almost one map up to some equivalence, and somehow, what is this equivalence? Well, that's immediately it's not clear, but there is so-called Alexander's streak, which gives us a hint. And what's Alexander's streak? Well, this is kind of topological lemma saying that if we have two closed disks, D1 and D2, we have two homomorphisms between D1 and D2, such that these homomorphisms coincide on the boundary, so they completely coincide. And then this claim says that we can deform one homomorphism to another continuously without changing them on the boundary. Well, and a more fancy way of saying it is that these two homomorphisms are isotopic relevant boundary. So this lemma, it basically says that then we will have isotopy, word isotopy at some point. Yeah. So now let me start formulating the things precisely. First of all, we need a notion of topologically homomorphic map. And well, informally saying is that if you have a friend who is pure topologist, you can bring him, I don't know, all family of all entire maps and family of all topologically homomorphic maps. And if he or she can distinguish these two families, then you bring him topologically homomorphic map. So, but well, kind of this is map which is continuous, open, discrete, meaning that fiber of each point is discrete. And well, one extra condition, which is technical, and I don't want to talk about it, but if you ask me at the end, I will ask. Yeah. So this is really just map which topologically looks like entire map. And here I write it like this, like in a strange way, because there is like convention in order, like if I write here from C to C, it means that I'm talking about homomorphic map. So it has to do something with complex structure. If I write like this, it means that this map is just topological. It's topological, it's continuous map. So yeah, it's just conventional, so easier to distinguish where we talk about homomorphic maps and where we talk about continuous. And in fact, for this topologically holomorphic maps, we can formulate all the lot of concepts from entire maps. We can define what is, I don't know, what is singular value, and we can define post-singular set, and all these concepts would work perfectly well for this map. For example, what is critical point of topologically holomorphic map? Well, that's point so that our map is non-locally injective. So, in fact, a lot of things which work for holomorphic maps, in fact, they have,
What do you mean by discrete?
by discrete, I mean that if I pick a point in the target and I take its preimage, the set will be discrete. So that yes, there's a preimage, the fiber will be discrete. So, and yeah, and that's why if you consider this topologically holomorphic map, we can define what is post-singularly finite in the same way as for entire maps, and we call topological.
I have one question.
Yeah.
So I assume the first definition, I understand you don't want to explain this technical condition. So I want just a question. I think every holomorphic map is topologically holomorphic.
Indeed, yeah.
Is anti-holomorphic not topologically holomorphic?
Okay, you got me. In fact, this was about preserving orientation.
Okay.
So yeah, indeed, we want. So if we forget about this condition, then every anti-holomorphic map is also topologically holomorphic. But we kind of want to work with topological models of holomorphic maps.
Okay, so this mysterious condition somehow gets you rotation preserving.
Orientation preserve, yeah, indeed. So we kind of well, yeah, but this is good question. Yeah, and here also I have one mysterious condition. Well, you can try to guess. Yeah, well, I've answered that. So we call topologically holomorphic map Thurston map if it's post-singularly finite. Well, this is in honor of William Thurston, who will probably started all this business. So this Thurston map is really like topological models for our post-singularly finite entire maps. In particular, every post-singularly finite entire map is Thurston map. So when we think about Thurston maps, you can think about kind of these topological pictures. Yeah. And so this is really, when I say combinatorial model, normally I mean something like Thurston map. And now I'd like to formulate what it means that Thurston map behaves like post-singularly finite map. Because, of course, we have in dynamics, we normally say that one map is the same as another if they are conjugated by something. But here we need weaker notion, which is called Thurston equivalence for Thurston maps. So maybe for combinatorial equivalence, we say that two Thurston maps are equivalent if they are kind of almost conjugated. What it means to be almost conjugated? It means that, well, if you have usual conjugation between maps, like here and there, we have the same homeomorphism. But in this case, so we have one map, Thurston map, another Thurston. Here we have two homeomorphisms, H1 and H0. So in fact, this H1 and H0, they are equal on this set PF, post a singular set of Thurston map. So this map F and G, they are indeed conjugated in usual sets on their post-singular sets. But outside of post-singular sets, well, they are not exactly conjugated, but by the definition, this H1, H0 and H1, they are isotopic rel PF. Means that, well, they are different, but kind of we can isotope them. We can a bit continuously deform them so that we actually get the same map. So really, the idea of all the Thurston maps is that we don't think about them like as maps. We think them as maps up to isotopy. So really, when you, I don't know, once again, have this picture, when you draw it, you don't draw exactly these curves. You draw them up to isotopy. So really, it's kind of, they're very flexible maps anyway. So that's why we have this very weak notion of equivalence. So really, they on post-singular sets they are conjugated. We know that post-singular set is something very important for our maps. Now, post-singular sets they are conjugated. Outside of post-singular sets, we can a bit deform them continuously and get the same actually conjugated maps. And well, when I was saying that some combinatorial model or some Thorsten map is realized, it means basically that this combinatorial model, this Thorsten map, is combinatorially equivalent to some post-singular finite entire map. So the question basically, and it's a kind of big question in Thorsten theory. So whether if somebody gives me this kind of, I don't know, some map like this, defined like this, and the question is there a polynomial or entire map which realizes this picture? And because there are a lot of examples, not a lot, but there are examples when this thing is realized and when there is no, we can draw a picture such that there is no entire map that provides this picture. And well, as I say, and it's we ask whether Thorsten maps, so purely topological maps, are realized, are Thorsten equivalent to some possibly.
If from the picture like this, do you see immediately whether if it's realized and it's do you know immediately if it's realized by polynomial or transcendental function? Is it's distinctly seen from the picture?
Well, depends on the picture, of course, because but normally we can see, because for example, for entire maps, if you take some graph, it's for transcendental maps, if you take graph and take its preimage, it will be infinite, because
so you don't collapse with whatever the preimages that are not on the orbit, you don't.
No. Yeah, well, so of course it kind of depends what you mean by picture, but if you kind of take a graph and you take whole preimage of this graph, for transcendental maps, of course, degree is infinite, and we will see some infinite construction here, but for polynomials, we will see something finite. So, so in principle, well, I think normally you can distinguish. Yeah.
Standard, you have a map F, and you want to correct it isotopically to have holomorphic. For example, I invent the word of polynomial. Then and take H0 identity, but then there's also identity, and G is not holomorphic. But you try to move, let's say, recompose G with some homotopic thing, so that H0 changes to H1, and you obtain already something holomorphic G. That's our goal. So I understand that you look for possibility to homotopically change G to obtain a holomorphic, to be holomorphic. Right? So saying about the possibility to find such diagram with G homomorphic means in fact that you want to change G homotopically so that there is this is holomorphic.
Yeah, I think this is the right definition, right intuition. I'm sorry. So we have like
a priori it is not possible. You can have semi-sphere where you have one quadratic polynomial, semi-sphere, upper semi-sphere where you have another quadratic polynomial, and on the equator you have the same. So it looks, but there is no way to sometimes to make it holomorphic.
Yeah, well, if you mean
You
like
want
maintenance,
to change the map asymptotically, and then you have a chance.
yes, yes. So, well, in fact, we have map G. We want to, I don't know, kind of isotope G to, I don't know, G prime, say,
And
and then G prime. Actually, I think we wanted to be.
chance to find a measure.
Yeah, so we want to. So
Change
that,
according.
so
In other words, to have a measurable.
yeah.
conformal structure.
Yes. So yeah, indeed. So it's really a kind of mixture of this homotopy or isotopy and conjugation. So we
It's not only that giving the zero, for example, identity, you can find H1 and G.
No.
But you need additional to
yes.
change. Conformal form.
So that's why also in a way that these maps are very kind of flexible in a way that we kind of think about them as well, we move them a bit, and for us it's all the same because up to this equivalence nothing changes. And well, any other questions? Okay, so well, maybe I'll say a few words. First of all, I need it for explaining the proof. How do we answer this question in social theory? How do we answer that our topological map is equivalent to holomorphic map? And just general idea how to answer it. And for it, I need to define the Teichmuller space of topological plane R2 with marked points A. So A is a finite set in R2. And well, the form
A will be the most singular.
yeah, indeed. For in our context, A will be post-singular set, but yeah, first I define it without connection to. But indeed, yeah, in all our arguments, A should be substituted by post-singular set. So here we have the set. How we formally define Teichmuller space? Well, this is all homeomorphism from this R2 to C, quotient by some equivalence relation. I'll try to say it informally. What this homeomorphism means? Well, having this homeomorphism, we can take like standard complex structure on C and pull back it on our topological plane R2. So really, these homeomorphisms is all different ways to put a complex structure on our topological plane. Well, you can talk about complex structure in some way. You can talk also there is equivalent definitions using hyperbolic metrics, but here I'll stick to complex structures. And so and here we care not only which structure we obtain after pulling back, but also we care how kind of we pull back by which homeomorphism. So what is equivalence relation? Well, we have R2A, we have two elements of our Teichmuller space. These are two homeomorphisms. Well, they're not actually elements of Teichmuller space, just some homeomorphisms to see. We say that these things are equivalent if they exist affine map like this, such that it maps this set onto this set, so it sends image of marked set by Phi1 onto image of marked set by Phi2. Basically, existing of such affine map means that if you take complex structure from here, pull it back by Phi1, and if you take complex structure here, pull it back by Phi2, we will obtain the same complex structure well up to isomorphism. But here,
what do you mean this complex affine map M for? If you have A, which is these 2 points, then must change the coordinates, must keep these 2 points the same, and well, it is just identity.
but if one is a homeomorphism, so it's not a complex.
You have Phi1 and Phi2 is a topic. You have A, so A during the isotopic. And if you compose with complex affine, you compose with identical. These 2 points, 1 point.
But what do you mean A stay the same?
Is the information is the same as it is to find the how this define the same.
Oh, maybe I.
The image of A does not have to be A.
No, but he assumes it is.
No, but
It can be contained, for example.
wait.
When it was critical set, you just take one image, go to the other.
Yeah, and if it is at least to find them,
but
it must be.
we can take some homeomorphism from R2 to C. Not just like C. And we can take another homeomorphism which is recomposed by a fine map.
Okay, but will these homomorphisms keep A invariant?
No, not necessarily.
no.
So yeah, we so they are equivalent if we first of all can put so that the A is the same.
Okay.
And second condition is that then we can isotope them. So
Don't assume A is the same.
no, A is just homeomorphism that can map A to whatever. But we say that it is equivalent if we just by a fine map we can make the images of A the same.
Okay.
And actually it means that pulling back like complex structures from this C here and by this C there, it will be kind of up to isomorphism, it will be the same complex structure. But also we kind of care how we pull it back, and that's why we require also that kind of this diagram commutes up to isotopy. It means that and that thing are isotopic. So yeah, and morally it's really like at least how I think about this Teichmuller space is really how we did all possible ways to put reasonable complex structure on the plane up to certain equivalence. But yeah, and now I want to say like why we actually introduced Teichmuller space. Well, because if you have a source and map F, we can associate for source and map, we can associate another map called source and pullback map or sigma F, this sigma F, which is defined on the Teichmuller space marked by post-singular set of F. And how I'll try to explain how this sigma map works. So suppose we picked just some point in Teichmuller space. It is class of equivalence of homeomorphisms. Well, homeomorphism phi. So we can look on this diagram. Here we have this homeomorphism phi, and here we have our map F. So we take a complex structure from here, pull it back. So now we have complex structure there. And well, it's non-obvious, but through topologically holomorphic maps, we can also pull back structure. So we pull it back there. And now we have R2, which is simply connected, non-compact surface. Well, now it's reverse surface. And well, we know that every simply connected non-compact surface is by the uniformization theorem is equivalent to hyperbolic plane or complex plane. Yeah, and in fact, in this case, it will be equivalent to complex plane by the condition I didn't tell you, but with some technical, we need to require some technical conditions, so there is this phi to see. And now you can see that this homeomorphism, it was a point in Teichmuller space, but this homeomorphism is of the same kind. It's also homeomorphism from R2 to C. So it again defines the point in Teichmuller space. We also can close this diagram by just going like this. And in fact, this map will be entire. So kind of, yeah. So, and of course, we need to check that well, this kind of if we kind of that this map is consistent with equivalence relation, but well, it can be done. So, and we define, well, this is how we define this pullback map.
Actually, after
The other.
trying to think, you don't need any quasi-conformality. You just pull back, you have isolated points, plane with isolated, and extend through these points of
Yes.
structure. up. And then again, straight in again. Straight.
So in principle, in this case, we can,
And you have G.
yeah, G will be entire. And yeah, in this case, actually, we can really talk about just homeomorphisms. Well, I think Kostya was talking about not post-singularly finite maps, and that's why in his context,
I just wanted to say that think about phi as it's just removing singular isolated.
Yeah, so yeah, indeed, we can think about all of them as quasi-conformal, and it's normally it's not
Structure by just taking the same atlas.
So maybe I'll give also a brief comment what actually is this formal definition, what actually it means. It means like really we are kind of taking the complex structure, pulling back, uniformize it. So really it's formally it's more complicated, but it's really like, well, it's a pullback map. That's why it's called pullback map, because what it does, it just pulls back and then uniformizes or yeah, straightens or yeah. And I have to say that, already we have seen such diagram in more precisely, well, not exactly such diagram, but very similar in the definition of source and equivalence. What we had in source and equivalence. I'll just redraw it. We had this map. We had these two homeomorphisms H0 and H1. So what I just wrote is just definition of source and equivalence for saying that map F is source and equivalent to map G, which is post-singularly finite. And here H0 and H1 are isotopic, well, relative here. And if you compare this diagram and that diagram, well, we can actually make a conclusion that if we leave this H0, this is also element of Teichmuller space, by F, we obtain H1. So this is, but also we know that H0 and H1, they are isotopic. It means that they define the same point in Teichmuller space. So this is just H0. So what I have written here is that H0 is just a fixed point of this sigma F. Yeah, and well, actually we can formulate it as if and only if condition, so that source map has a fixed point. If and only if this map is equivalent to some possibly finite entire map. In fact, what I have to say that this Teichmuller space, it has a natural structure of finitely dimensional complex manifold, and sigma map is a holomorphic map with respect to this structure. So indeed, we are doing once again holomorphic dynamics. So we have a complex manifold, we have an analytic map, and we are interested whether this map has a fixed point. So, well, one can say, well, this is some topological questions, but now they are reduced to the proper holomorphic dynamics. And in fact, this map has at most one fixed point. And in fact, this implies that if this source of map F is indeed equivalent to post-singularly finite entire map, it means that, there is only one map like this up to conjugation. So at some point I was saying that this picture with rabbit polynomial, it actually defines rabbit polynomial. And this is exactly the, kind of precise way of saying it. If some combinatorial model is realized by something, then this something is unique up to a finite conjugation. Yeah, so yeah.
Do you have in this context something? Probably you have hidden in your mysterious condition something so that it has most one fixed point that you don't have this, which is third examples like about a hyperbolic orbifold or something.
Well, for polynomial, well, okay. Well, no, I have hidden different thing, but here, well. If you consider, I don't know, Chebyshev polynomials, whatever, they still have one point, even though they have hyperbolic orbifold. So for polynomials, we have, so these weird flexible lattice maps, they appear only for rational maps. So this is indeed in when F is kind of some entire map is this true.
So it's strictly contracted.
Or well,
in your case.
Some iterate of it is strictly contracted. So yeah, but yeah, I have to say maybe what Kostya was asking that normally, this Teichmuller space also has a metric, well, metric in a usual sense, such that sigma f is contracting with respect to this metric.
But now maybe you are a smaller phase than Teichmuller to measurable. Metric, you need to have quasi-conformality over the.
No, but in this case it's equivalent because it's postsingularly finite case there it's
Yeah, so yeah.
In this case.
Yeah, so for us, actually every homeomorphism, it can be isotope to quasi-conformal or to diffeomorphism. So here, that's why I'm so freely jump in, say everything's topological, but so in this case we can afford it. So yeah, the reason is of this theorem is that this map is contracting, and normally it's even strictly contracting, so there is only one fixed point. Yeah. Well, maybe any other questions? Okay. Well, I'll try to give now. Up to you.
Yes.
Okay.
That's one person. I also find.
Well, so I think at this point I introduced all the tools I wanted to introduce, and finally I can say a few words about like some ideas of proof. Yeah. So as I was saying, in sourceless theory, we normally, well, not normally, but quite always, we start from constructing topological objects and then proving that they are actually somehow holomorphic. And here we do the same thing. Like, if you remember, our goal was to construct like post-singularly finite, for post-singularly finite map, construct sequence of post-critically finite polynomials so that they have the same dynamics of singular values and they converge. And well, kind of a priori it's not clear how to do, so let's try to do it in a more topological context, just because, well, in topological it's more flexible, it's easier. So what we are doing, we have some transcendental source map. So it's so just source map, something topological, and we construct sequence of polynomial source maps. Yeah, I have to say that we can distinguish, well, transcendental and polynomial source maps by just looking on the degree. If degree is finite, then it's polynomial. Degree is infinite, then we say transcendental. Now we construct such sequence of polynomial source maps so that they have the same post-singular sets. And well, they are equal basically on this post-singular sets. And well, another well question is that if you construct such a sequence, we want to say something about convergence. But when we talk about source maps, it's not clear what convergence means, because normally we think about them up to isotopy, so we it's not very reasonable to talk about, I don't know, point-wise convergence of source maps. It's not very natural. But I have introduced this sigma, well, of course, it's not me who introduced, I introduced during my presentation, the sigma maps. And sigma maps are kind of, well, they're more geometrical objects, they're defined on this, I don't know, complex manifold with metric. So we can really think, well, we have a Thurston map, we have associated sigma map, and the sigma map says a lot about the Thurston map. So why not do actually compare sigma maps if you can compare Thurston maps? And well, this is what this theorem says. It's, well, the first theorem, it says that basically, yeah, there is this sequence with the same dynamics of singular values, such that sigma maps converge. And I'll try to explain how actually to construct this sequence of polynomials of n. So suppose we have a transcendental Thurston map, and yeah, we have already, I have already shown some pictures with these rows, graphs, and their images. And well, we can do the same thing. We have some transcendental Thurston map. In this case, it has two singular values. So we can take a rows graph and we can take its preimage. I just chose some example. Here we have the following preimage, which is infinite. So here it kind of continues periodically here and there. And well, and this picture basically, well, defines our Thurston map up to equivalence. And like, well, as already it was in the answer of Costa's question, transcendental Thurston map, they will have infinite preimage. Polynomial Thurston map, they will have finite preimage of this. So, and now we think, okay, we have something with infinite graph, and we have to approximate it with something having finite graphs. So why not to try a very silly idea? We are just taking finite part of this graph like this. I just took this part and copied here. And well, actually what is written here, it doesn't make sense. This kind of thing does not define a map, because if you have a Thurston map, if you take a graph outside of a singular set, the preimage should cover initial graph, and here it does not cover. But we can just add a small petal here. And now this picture defines a map. In fact, in this case, it's basilica. We can try to continue this idea in the following way. Here we took, I don't know, this part of the graph originally. Well, it's here, and we just added one petal and obtained a map. And then we can take bigger and bigger parts of graphs. For example, here we took, well, this kind of part of the graph. Well, and of course, to obtain polynomial, we had to a bit adjust this graph. Now this defines some topological polynomial. It now has a critical point, for instance, of degree 3, and so on. And we continue. We take even bigger piece of graph. We a bit kind of add something to it, and it defines a new topological polynomial. And we go further and further. And you can see, like, just on this, like on this picture, that kind of these graphs, they look more and more as original graphs.
It's like substitution, right? Place at tail, split in two tails.
Yeah. So yeah.
So you substitute two tails.
Yeah, in a way, yeah. So this defines a sequence of topological polynomials, well, we can, and their graphs getting bigger and bigger, and kind of in the limit, which we can define precisely, this will look like this. Yeah. I think this idea is pretty natural and somehow illustrative. So we just, I don't know, play with graphs and so on. And in fact, this is how we construct this sequence of polynomials Pn. And this construction, of course, I demonstrated it for a particular case. But if you have arbitrary graph, you also can just take a big piece of graph and then explain that we can add a bit, just something, just a bit to have a polynomial. And yeah. And
It's always, maturity is always only one. This, right. When you say you're in general.
well, here we basically taken the graph and add in only one edge. But in general, we will add maybe more edges, but they will be kind of, we can imagine that this point is kind of base point. Yeah, so we are taking a part of graph around this point, bigger and bigger. So kind of what we add, it will be far from the base point, and in infinity it will disappear. Like here in this sequence, if we kind of look at this part of graph around this part of graph, kind of this thing will be kind of further and further in graph, and it will disappear in infinity. At infinity, so this kind of edge. Well, this is a very hand-wavy and informal explanation, but all what we add, it will be kind of far from the chosen base point, and kind of. So, but this can be generalized for arbitrary post-singularly finite map. Yeah. And well, the more complicated, well, this is how we define graphs. We can actually check that all these graphs will have the same dynamics, of all these polynomials will have the same dynamics of post-singular set as original map. So this first requirement is satisfied. Well, we need to prove the second thing. And I don't know, probably I'll skip it. So because, well, probably, I don't know. Okay, I'll skip it. So well, I feel that I'm running out of time. So well, so well, I don't know. Okay, it's tempting, but I don't know. Yeah, well, maybe let me. Yeah, let me. You can ask me then, and we can discuss if you want, of course. Don't insist. So and now we.
Combinatorial is
Yeah.
understandable, but next.
Yeah. So we have a we have a theorem which says about like Thurston maps, combinatorial, like topological maps. And now we want to prove something in complex context. So basically, I just restated the theorem that we had at the beginning. So we have a now post-singularly finite entire or complex holomorphic map, and we want to obtain the sequence of these polynomials so that they converge to F and they have the same dynamics on post-singular sets. And what we do, well, we want to use somehow this combinatorial version. So, and well, we use it and we construct sequence of polynomial Thurston maps such that the sigma maps converge to sigma map of F. So this is just by previous theorem. But these polynomials, they are topological, so and we want them to be complex. So we need to somehow say that they're complex. And basically, what we are going to use this effect. And I once again remind you that that some topological map is realized if and only if its sigma map has a fixed point. So really, we need for these polynomials Fn to prove that this sigma map has a fixed point. But we at least know that this map has a fixed point. Why? Because F is a post-singularly finite entire map. So we started with realized map. We started with complex map. So corresponding sigma map has a fixed point. So now we know that limited map has a fixed point. In fact, we know that this map, they're kind of contracting. And basically it implies that these maps will also have a fixed point for sufficiently large n. I denote this this fixed points by tau n. And moreover, we can show that these fixed points for sigma fn, they converge to fixed point for F.
Convergence actually exists.
Yeah. So this is it's yeah, this kind of general.
You say that contraction. So why sigma fn? The same reasons which you didn't explain why.
I didn't explain why this map are contracted. Yeah.
You didn't even explain why sigma f.
Well, I wish I could, but no, it's a general fact.
Maybe for sigma n you don't need an test on condition.
No, if you have f, sigma f, where f is any Thurston map, not necessarily complex, it's always still contracted. It's maybe non-uniformly contracted, so we cannot apply the Banach fixed point theorem or something like this. So it can be, I don't know. So, but it's always contracting non-uniformly.
So no additional condition.
Yeah. This is a general fact.
Sigma fn you need to verify test.
Yes. So really, like the Thurston condition is that it will have a fixed point.
Yes.
Which so but if you have a kind of complex complete space and we have contracting map, it's not necessarily that it has a fixed point. Well, it's uniformly contracting. I think it will, but if it's not uniformly, it's not necessarily. But so it's always contracting and still cannot have a fixed point. But this is a general fact that all of them will be contracting, and well, sorry that I didn't explain, but yeah.
Maybe sigma fn and additional condition because it is close to sigma f.
Yeah. So yeah.
Is good.
So basically, to obtain existence of fixed point for these maps, we just need to know that we converge, that this has a fixed point. And well, there's some generalities that Teichmuller space is not a very bad space, it's complex manifold. So you had a question? No, already. So really here we are using that we started from complex map and then use some, I don't know, generalities to prove that this also is a fixed map. And also important that it's in fact kind of not a difficult statement, but it's important that so they will converge. And so this, so we know that these all fn's, we started and constructed them combinatorially, but they are all realized. And they give us polynomials Pn, which are kind of candidates for this theorem. Well, it's easy to verify this condition for Pn's because we know that similar condition holds for Fn, and Fn and Pn, they are equivalent. Well, it's a bit more complicated to verify that they will actually converge, but it's also can be done. Well, in particular, it's important that kind of these polynomials, they are coming from very kind of close points in Teichmuller space. So this is the idea. So any further questions about this slide?
Why sigma is contracting? Explain it.
Well, it's just question.
Maybe it's not so clear.
Yeah, well, it's not so trivial, and
well, just contraction is real, but strictly contraction is not
Strictly.
yeah. So, but yeah, for this, but there is a kind of. Well, the reason is that there is a good Finsler metric on Teichmuller space, and that they. So maybe. So, but okay, I assume it as a general fact, like so. I think Kostya can confirm that I didn't lie. Okay, not. It's up to him. Yeah, and maybe. So this is well, almost all that I wanted to explain. I just want to say a few general words. If sum up.
6 factors.
Well, this is actually yeah. Some of them they are not. Oh, you see, it's and thank you. So we are not so far.
5 pages, thank you, that's it.
Yeah, no, there is yeah. These pages are bonus, so now you got interested, so I can show them afterwards. Yeah, so one of the, as I was saying, that kind of course we know that transcendental maps are much more complicated than polynomials, but and transcendental Sortland maps are much more complicated than polynomials, and there's no transcendental sigma maps are more complicated than polynomials, sigma maps. But in these two theorems, we are proving that all of these objects, they are, in fact, can be viewed as limits of polynomial objects, and not just limits, but like reasonable dynamical limits. And well, for me, this is hope that so we can move our what was successfully done for polynomials to try to move it to the kind of limits to transcendental maps. Maybe I just will mention one problem I'm also interested in, just very briefly. I have already mentioned it, and this is a problem of checking whether the some map is realized. So here we actually prove that some maps are realized, that these polynomials are realized. But here we knew that their sigma maps converge, so we kind of, but in general situation, I can imagine that somebody gives me combinatorial model and I have to check whether it's realized. Of course, I can take sigma map, take Teichmuller map, and start iterating on Teichmuller space. Well, but it's not so easy to do. We need some simpler conditions. And actually, some simpler conditions, they exist. I will not explain them, but there are some very kind of topological conditions. So like you have a combinatorial model and you have to check there is no simple closed curve with some properties. So it's very simpler topological condition. Still not trivial, but much better than iterating something in Teichmuller space and analyzing it. And this condition was obtained by William Thornton and written by D. Hubbard, and for polynomial and rational Thornton maps. And now, but the same question can be formulated in transcendental context. And it happens that this proof, there are several essential places where it cannot be generalized to transcendental context. Well, but people thought about this problem, and the first result was obtained in a paper by Hubbard, Schleicher, and Shishikura. They considered particular family of Thornton maps, and they provided similar criteria to polynomials. They provided a way how to check that these maps are realized or not. But this was for particular family. Well, then there was a recent thesis of Dirk Schleicher's PhD student.
Multi-error.
Multi-error. Yeah. Well, in fact, these are maps that have no critical points, and then they have finitely many asymptotic tracks. Well, they are called multi-error maps because if such map is such map is complex, it can be written in the following form. So it's kind of almost this error function, so this is an error function which is in the normally people in probability study, but we can view it also as transcendental as entire map, and it has no critical points and finitely many asymptotic tracks. So this is why they're called multi-error.
P is polynomial.
Yeah, P is polynomial indeed. Yeah. So if such map is holomorphic, then it can be written in that form with integral. So this is why they're called multi-error. So this is still some particular family, well, much bigger than just exponential maps, but and for them the result was obtained. And but there is still a lot of work to do, and somehow. For me, at least, these two theorems I mentioned, they provide certain hope that if we succeeded for polynomials, maybe we can also further succeed for transcendental maps as well. At least I hope to provide some reasonable criteria how to understand whether given transcendental source map is actually holomorphic source map. Well, and this is just to mention it, and I think that's it. Well, thank you a lot for
Are there any questions? Or already asked? I have one question. Could you please say a few more words, spend a few words about how you still solve the type problem so that you don't have this unit structure?
That's a good question, and
so you don't under iteration you can get if you do R2, then you can get
that's how I solve it.
Yes, understood.
No, I just require that the source map has a parabolic type. So maybe I'll just extend a bit what Kost asked. There is following, it's called type problem, and this is the following thing is if you have a topologically holomorphic map, and we put here a complex structure, so that it's complex structure or complex plane. By this map, well, it's non-obvious, but we can pull back this complex structure. So that they may be like, so we put some complex atlas A, so that this thing is basically isomorphic to C. We can pull back this complex atlas to here. We have some different complex atlas. And we ask the question. So we have now Riemann surface, which is non-compact and simply connected. Then it's either C or D. So, in this case, we normally call that it's parabolic type. Our map is of parabolic type, and this we call map of hyperbolic type. And and there is actually definition of sigma map. Remember, I said that here we actually equivalent to C, not to D. And actually, this was because I assume this condition of parabolic type for here.
So, but what do you mean by parabolic? It's just that this situation does not happen. It's a definition of parabolic, or is that not
well, parabolic map, at least in the finite type context, it means that if you put here C, then we will get C. And if you put hyperbolic, if you put here C and get here D.
So you assume you have C.
Yeah, I assume that I have C.
No, but then it goes like you exclude like bad situations by not considering them.
Yeah, but they don't have. If you not assume this, it's not meaningful to ask this question because because in this definition, well, okay, maybe here. So we want our maps to be like maps, post-simplified entire maps. But if it has parabolic, if it has hyperbolic type, it wants to be a map from D to C. So it's not like dynamical system based.
Maybe you already have this realization via F, right? So it sort of converges in a way. You want to be construct like this structure, but because you already have a fixed point for your final sigma F, to which you construct approximations. Because you construct the sigma Fn convergent to sigma F locally uniformly, uniform. So you don't get this hyperbolic type because you already know that your final sigma F is parabolic.
Yeah, well, but yeah, it's parabolic type, and polynomials always have parabolic types.
So, oh, it's polynomial, of course.
So yeah, well, we know that there are kind of holomorphic maps from D to C,
Because it's political.
and some topologically holomorphic maps, they want to be holomorphic maps from D to C, and some want to be from C to C. And from D to C, we don't consider them because they're not kind of, you cannot iterate them. Well, you can iterate them, but it's something strange. Yeah, that's was what I have hidden. Yeah.
If you don't mind, I have one more question to ask, maybe. So you construct this, well, you have initial map F, transcendental time, but for example, you can, what happens if you construct, take some like topological model of this function, which you don't know it's realized or not, but is it still possible to, in some sense, approximate it by polynomials, even if it isn't necessarily realized? Well, in the sense that you approximate sigma f by sigma fn.
Well, this construction works for all maps, even non-realized.
Okay.
So this well, when we talk about topological maps, we have no assumption of topological maps. This can be abstracted or map that can be realized. We don't care. Sigma maps still converge.
Yeah. Okay. So, Sarah, question. Okay, let's thank Colette again.